Hello, my name is Huang. I'm an undergraduate student at Lanzhou University. The paper I will be presenting today is titled Optimized Gait of Climbing Caterpillar Robots in Terms of Enhanced Obstacle Crossing Ability and Stability. And my presentation is consisted of 5 parts: introduction, the literature review, the methods, the results and discussion, and the conclusion. Firstly, I will introduce my topic background. Climbing robots have excellent working performance in harsh conditions across various fields, and among them, modular caterpillar robots they have exceptional traits such as high flexibility and distributed weight, and they are inspired by caterpillars who move by locomotion waves. And stability and obstacle crossing ability are two of their crucial properties. And the purpose of this study is to enhance the stability and obstacle crossing ability of the caterpillar robots while optimizing the locomotion wave parameters. In the literature review part, I basically reviewed how researchers established the kinematics modeling and how they evaluate the properties of the robots, basically the obstacle crossing ability and stability. And my main conclusion is that although the stability examinations in various studies are quite similar to each other, there are few unified quantitative approaches to study the obstacle crossing ability. And therefore, my innovation point is that I want to derive a unified method to quantify the obstacle crossing ability, and I want to enhance the obstacle crossing ability by using some optimization methods where the objective function is the quantified obstacle crossing ability. The outline of part 3 is that I use the static optimization methods to enhance the obstacle crossing ability, and I used dynamic optimization methods to enhance the stability. And in static optimization, I first quantified the maximum obstacle crossing ability, and I will illustrate how to establish the optimization equations in the full-link wave case and how to extend it to the n-link wave case. And in the dynamic optimization part, I will show you the dynamic gait in the form that could integrate the forward locomotion and the obstacle crossing locomotion, and how to select the link slopes in using dynamic optimization methods. um, um, in the static optimization, the maximum obstacle crossing ability is quantified as the wave's maximum inscribed semicircle, and this is meaningful in terms of universality and practicality, because in many previous studies, the obstacles were simplified as regular blocks, but real obstacles have much more complicated morphology, such as the pits and bumps on cables. However intricate the morphology is, they can be circumscribed by a semicircle. So this shows the extensive range of application of this quantification method. And also, this method is practical because zero contact and interactive force between the robot and the surface can be achieved in this method. And now I will illustrate how to establish the optimization equation using a full-link wave case. So O is the center of the inscribed semicircle, and D means distance from the center O to the link. And because the optimal condition is realized when d1 equals to d2, so we can set d1 as the objective function that needs to be maximized, and set d1 equals to d2 as constraint condition 1, and constraint condition 2 and constraint condition 3 is set so that the shape is a convex shape rather than a concave shape. And this set of equation can easily be extended to a n-link wave case. And in the dynamic optimization part, this picture shows the whole process of a caterpillar robot crossing an obstacle while climbing, and it can integrate obstacle crossing locomotion, forward locomotion. And the following shows how to calculate the link slopes from state 10 to state 12. So this picture shows the transitional process from substage 2 to substage 3 in figure 2 in the falling wave case. And the basic idea is that if we want to minimize the torque induced by gravity, which is the main source of instability, we want all the links to be as close to the climbing surface as possible at every time node. And then we can calculate the link slopes as a function of time. In the results and discussion part the static optimization results include the optimized wave shapes and the varying pattern of stability and obstacle crossing ability in two cases, and also the focus of N-link wave optimization results. And the dynamic optimization results include the dynamic gait in the form of the superposed link positions, and also the varying pattern of stability during each movement unit. So this picture shows the optimized wave shapes in case 1, where the length of each link is constant, and in case 2, where the wave's total length is constant. And this picture shows the relationship between the maximum obstacle crossing ability and number of links, and also the relationship between the moment induced by gravity, which is the main source of instability, and the number of links. As can be seen from it, in case 1, increasing the number of links can largely increase the maximum obstacle crossing ability at the risk of arising the instability issue, while in case 2, increasing the number of links can hardly increase the maximum obstacle crossing ability. In other words, given that the total length of the link of a wave is constant, dividing it into many links can hardly increase the obstacle crossing ability. And the following shows how to focus the optimization results in the case of the wave involving many links. So this picture shows the relationship between the link angles and the link order, and we can use linear regression to plot this figure. It can be observed that all the lines intersect at this point, and also the lines x intercepts can form an arithmetic sequence. So we can easily derive this equation. And the dotted line shows the focus result of the link involving 11 links, 12 links, and 13 links, and they are very close to the results that we can calculate by directly solving the optimization equations. And here are the dynamic optimization results. This picture shows the dynamic gait in the form of the superposition of link waves, 4-link wave case, the 5-link wave case, and the case of 10-time nodes and 60-time nodes. And this shows the varying pattern of stability in each movement unit, and it can be observed that the caterpillar robots are more stable in the latter half of the movement unit, and that generally the 4-link wave case is more stable than a 5-link wave case. And the final part is the conclusion. First I'll talk about the significance. This study proposes a quantitative measurement of the robot's maximum obstacle crossing ability, and that is the size of the robot's maximum inscribed semicircle. And this is meaningful in terms of universality and practicality. And in static optimization part, the relationship between the obstacle size and the optimal wave parameters are derived, and and the results of waves with large numbers of links can also be focused via data analysis, which greatly reduce computational cost. And in the dynamic optimization part, the combination of climbing and obstacle crossing locomotion is achieved via, triangular supplement wave, and stability is enhanced by minimizing the moment induced by gravity at every time node. The limitation is that the robot's climbing efficiency may be sacrificed, which is also a crucial property of robots. And that is the end of my oral presentation. Thank you very much for listening.